Hi everyone, I'm Enna, and today I'll talk about our work on multi-agent evolution via dynamic skill selection, which is a joint work with Oregon State University, Intel, and Microsoft. In real world, we see lots of agents coordinating with each other, like from our homes to industry, from our streets to air traffic management. We also see their applications in critical environments like search and rescue and planetary exploration, where they have additional advantage in terms of maximizing the coverage and failure management. But multi-agent learning is a pretty challenging problem. One of the challenges that comes in multi-agent coordination is from the sparsity of reward. With reinforcement learning setup, it becomes extremely challenging and sample efficient as the sparsity of reward increases. Let's look at an example of a single agent case. We have an agent and we have a goal state, and agent receives a reward of 1 only when it reaches the goal state, otherwise the reward is 0. Agent can take multiple trajectories to achieve that goal reward of 1. With sparse reward, it becomes difficult for an agent to identify which action at what time instant was actually responsible for achieving that reward of 1. In addition to it, in multi-agent coordination setting, we have an additional problem, which is called structural credit assignment problem, which is associating agents' actions with sparse and delayed team reward. Now let's look at an example to understand this better. Consider this game of soccer where the goal of a team is to win the game. But this is a very sparse and vague way of representing the goal. In order to maximize this reward, agents have to take hundreds and thousands of actions before getting any feedback signal to learn from. And this makes the learning process extremely challenging and sample inefficient. But fortunately, in most of the real-world tasks, agents have access to few local rewards, which they can compute from their own perspective of the environment. And these rewards are local to each agent, they are dense, and they can be optimized pretty easily. For example, here in case of soccer, agents can learn to dribble the ball well, they can learn to trap the ball well, pass the ball well, and so on. These are some agent-specific rewards which they can bootstrap from in order to optimize more sparse team reward. But the problem is, these rewards are not always aligned with the team objective. For example, one skill, which is perfectly passing the ball, is a very useful skill to have. But overdoing it could be extremely harmful for the team objective and team may lose the game. Now, there are a couple of existing work along this line which leverages the local rewards to solve complex multi-agent coordination problems with sparse reward. And one such approach is scalarization, where team reward is formulated as a linear combination of set of local rewards, and team optimizes that linear combination. But that linear combination cannot always capture the intricacies of the problem that are dynamic and changes with different phases of the task. Another solution is to use some agent-specific reward shaping, which involves using complex nonlinear functions to shape the rewards in order to optimize the global reward. But mathematically formulating those agent-specific rewards, which can capture the complex coordination behaviors, is very difficult. And it requires a lot of domain knowledge, fine-tuning, which makes it more not scalable as well as not generalizable. So the contribution of our work is a bi-level optimization framework that leverages set of local dense rewards to optimize sparse global reward. And the way it does is by learning and dynamically selecting the most optimal local reward from a portfolio of local rewards without requiring any form of reward shaping. Let's look at how our model works. We have policies of each agent, which represents our team. We have n agents. And now we have m such teams of n agents. And this is what is called an evolutionary population. Then we take each of these teams, do a rollout in the environment. For each of these teams, we collect team reward towards the end of the episode, which team gets from the environment and stores them in the form of a fitness score of the team. Based on this fitness score, the selection operator selects the k most fittest candidates from the population of each agent, and then probabilistically perturbs them through mutation and crossover to create next generation of teams. And by doing so, a portion of teams with highest fitness is preserved as elite. At any given time, team with the highest fitness or the champion represents the best solution of the task. This whole block till now is a CCEA, which is also one of the baselines for our experiments. In our architecture, we have additional K policies representing each of, and where each of these policy represent a local, optimizes a local reward, which is agent agnostic. And we use policy gradient method to learn these policies. Now, to attain this sample efficiency in our architecture, we use the best of both worlds. We use sensitivity of global rewards in CCEA, along with sample efficiency of fast policy gradient based methods. So both of these optimizers, where one optimizer is trying to optimize the global reward, which is CCEA, and the local policy gradient learners, which are optimizing the local dense rewards, which are policy gradient methods, they talk to each other in some way via a shared replay buffer. We store all the data of rollouts by EA in this shared replay buffer. So here the experience tuple consists of state, action, next state, local reward, global reward, which is a team reward. And the local reward is nothing but a vector of rewards R1 to Rk for each of the k skills. And these local rewards are distance-based proxy rewards. And the reason they share a replay buffer is because it is being used to learn skills, because skill learning is being done by policy gradient methods. And they sample the experiences from this shared replay buffer to learn these policies. We use TD3, which is a reinforcement learning based policy gradient method, but we can use any other RL algorithm to optimize the local rewards. So these local optimizers learn the local skills from high fidelity dense local rewards, and EA learns to dynamically select the most aligned local reward at any given time step. So both these learnings are happening parallelly. So simultaneously, these local rewards are being learned by the experiences from the shared replay buffer, and the EA rollouts collect the samples and store them in the replay buffer. And both global level optimization and local reward optimization happens in parallel. Further, in this architecture, we have online learning of skills, which allows us to easily plug and play new skills to the portfolio of skill at any given time during training. So we can define any other local objective and can plug and play in this portfolio of local learners. So this model is also amenable for lifelong learning. Now, the key strength of MAEDyS is that it allows significant flexibility in designing the dense objectives corresponding to local skills and dynamically select the most aligned local skill for each subtask. To the best of our knowledge, we are not aware of any other technique that simultaneously learns a set of local rewards and dynamically selects the most aligned ones in complex coordination or multi-agent coordination settings. So now, after a motivating example of soccer, we now move to a more general framework of multi-agent coordination task for experimental purpose and problem setup. Now, this environment is motivated by space exploration task. Here we have multiple agents and we have a bunch of points of interest denoted by these rocks. And the goal of agent is to maximally explore, basically visit the maximum number of points of interest and collect rock samples here. Here we have a bunch of constraints. One is spatial coupling constraint, where reward will be given to each of the team only when the desired number of agents come together at a particular POI. So at a gray point of interest, we need at least 3 robots to come together. And at orange POI, we need at least 5 robots to come together to explore that. In addition to it, we have temporal coupling, where all these points of interest have to be observed in a particular order. So the order for this particular task is, let's say, gray followed by orange followed by blue. And along with satisfying the spatial coupling requirement of 3, 5, and 4 agents. So this is what the temporal coupling requirement of this task should be to achieve a team reward of 1. Otherwise, the reward will be 0. So along with CCEA, we have also tested MAEDyS with MERL and MFL, these 2 baselines, and we see that MAEDyS outperforms all other baselines in spatial coupling requirement tasks, temporal coupling requirement tasks, sparse rewards, and is more sample efficient and is also amenable for lifelong learning. Now let's look at experiments. So the way we have conducted experiments for this testing is using two temporal couplings. So one is 2 and one is 3. So by 2 we mean we have two types of points of interest and they have to be visited in a particular order, and by temporal coupling of 3 that we have 3 types of points of interest, and we vary the spatial coupling from 1, 2 and 3 for both of these temporal coupling requirement. Let's look at the first scenario in which we have just one agent and temporal coupling requirement is 2. And the way we define local rewards is go to POIA. So they are some distance-based proxy rewards. Go away from POIA, go to POIB, go away from POIB. And here are the results. So we see that MAEDyS outperforms MFL and CCEA significantly. And now let's look at the histogram of the reward selection. So here we see that we have just one agent and we see how the distribution of local reward selection happens. So if you look at the time step axis here, it represents the episode length. So we see that in the initial 20 or 25 step of the episodes, agent selects go to POIA local reward, followed by POI go to POIB local reward in rest of the time steps. And this is very much consistent with the human understanding of the task, that if the temporal coupling requirement is 2 and if agents have to visit POIE A followed by POIB, then we should select go to POIA followed by go to POIB reward and successfully ignore or reject other rewards. And this is what the agent does. Now let's look at a more complex scenario where we have two agents and spatial coupling of 2, temporal coupling of 2. And now this should be the desired behavior, that agent should form a team of 2. They should first visit POI gray followed by POI orange in a team of 2. And let's look at, and these are the local rewards. So we have same local rewards as before, but now in addition, we have 2 more local rewards. One is go to agent and then go away from agent, because now we have more than one agent. So now we see that MAEDyS again outperforms MFL and EA, and we see the distribution of reward selection. Agent 1 selects go to POIA followed by go to POIB, which makes sense. And agent 2 selects go to agent always throughout the episode, which also makes sense because agent 2 is trying to form a team, or it's trying to be as close as possible to agent 1 so that they can form a team of 2 and then visit POIA followed by POIB. So this is also consistent with our understanding of the task, and this makes it quite explainable. So now we move to other setting where we have 6 agents, spatial coupling 3, temporal coupling 2. Again, MAEDyS outperforms MFL and EA. And we see that agent 1, 2, and 5 forms a team of 3, and agent 3, 4, and 6 forms another team of 3, and they visit POIA, like 1, 2, and 5 visit POIA together, and 3, 4, and 6 visit POIB together, and they've completed the task. Now we have more difficult scenarios with temporal coupling 3, and I'll not go through that in detail. So we see MAEDyS outperforms in all such scenarios. So in conclusion, we saw that we introduced MAEDyS, a framework that leverages semantically meaningful local rewards to address complex coordination tasks, which involve spatial and temporal coupling. And it solves this by allowing multi-agent teams to dynamically select from local policies that are trained on different dense local objectives. And our future work includes incorporating learnable local skills along with user-defined ones in order to allow better diversity of local strategies, along with incorporating heterogeneous agents with different observability and action space. With this, I conclude my presentation and thank you for your attention.